We are now dealing with the least squares assumptions. We need to know when we can trust our results and when we cannot trust our results. That's why we have these assumptions. The OLS method gives us unbiased results given certain conditions. So let's get to it. The first of three assumptions is that the conditional mean of the residuals given a certain value of x is 0. What does this mean? It means that, for example, you have the scatter plot, okay, between x and y, and with this data, you can draw a straight line, the OLS straight line, and whether you choose x1 or x2, for example, the conditional mean of the residuals around this line is 0. So on average, the residuals should be 0, no matter where on this line you look at, okay? For example, or conversely, you can have this scatter plot between x and y, and maybe you have this line here, and you have an outlier. If you look at this section of x1, or you choose the value of x to be x1, then the residuals are on average positive, right? And whereas the residuals can be around 0 for other values of x, but in this case, we see that the y hat, the estimated line, is biased for certain values of x. Okay, so that's the point of this assumption, and if the x is randomly assigned, then the residuals and the x values should be uncorrelated. They should be independent. Okay, so this is actually in practice the most important assumption to consider. The second assumption would be that the pair of xi and yi, the pairs of x and y, are independent and identically distributed. They are IID. For example, it means that any pair of x and y, and any pair of x's and any pairs of y's are all independent of each other. So you can test that by looking at the covariance between x and y, and the covariance between different x's, and the covariance between different pairs of y's. They should all be 0. Okay, and it means that, well, if this holds, it means that all of these pairs, they have the same distribution, right? So you can have this the variance of x should be a constant, okay, and the variance of y should also be a constant. And the covariance between x and y should be a constant, okay? And this assumption should hold if we take a simple random sample of the population, that you look at one entity at random, okay, from the population. So you take random draws. Continuing, if the sample is not drawn randomly from the population, then this assumption might not hold, because the researcher might be biased towards drawing from a subset of the population. For example, if only rural schools are included in the sample while the population of interest is all schools, then this assumption is violated, because you only draw from a subsample of the population. So if the rural schools are somehow different from the non-rural schools, then this assumption is violated. And importantly, especially later in the course, this assumption would also fail if we have time series data, because often, or might fail if we have time series data, because often in time series data you can make a rule of association. It means that if you can, it means that certain lags of the variables might be correlated with the present value. So, for example, a price movement today might be correlated with a price movement yesterday. This means that this assumption is violated, and we will look into this problem when we get to the time series analysis. So basically, assumption 2, if you can make a rule, if you can make a rule of when the correlation or the covariance equivalently is different from 0 between certain parts of the data, then this assumption is violated. And the last assumption would be that large outliers are unlikely. So for example, I already mentioned that outliers in the previous assumption. Well, for example, if you have this data, but you have this outlier here, then you would probably get a lower slope on the estimated regression line, which means that the slope, the beta 1 hat, and the intercept beta naught hat would be biased, would probably be biased, either one of them or both. Okay, and you see from the graphical display here that an outlier on the ends of the data would affect the slope quite heavily, whereas an outlier in the middle of the data set, in the middle of the x value set, would affect the height or the level of the estimated regression line. And think about that. Think about what we do when we fit the regression line. We minimize the square of the residuals. The square of the residuals, which means that if you have this outlier, the square distance is a lot higher than for most of the other data points, which means that a number which is far away from the other data points would have a large effect on the slope and the or the estimation of the regression line. And mathematically, we just say that the x variable and the y variable should have non-zero but finite fourth moment. So we say that we have non-zero finite kurtosis, okay? And if x and y has natural bounds, then this is not a problem. If the data generating process is unbounded, then like a price process, then this might be a problem. We'll look into this when we do time series analysis. So, and this lastly, this outlier might just be because there is some errors in the data. Okay, for example, a person cannot weigh 500 kilos, right? So that would be like a test to see if you have an outlier, is to see where is the logical range of the data, and you have to know where the data is coming from to know this. So why do we care about these assumptions? I brushed upon it in the first slide. Two important reasons is that are that if these assumptions hold and the sample size is sufficiently large, then we can apply the central limit theorem. Sorry. By using the central limit theorem, we know that the intercept and the slope have certain distributions, right? They have a normal distribution. And why do we care about that? It's because we know how the normal distribution acts. We know how to calculate probabilities, which makes it easy for us to calculate probabilities around these estimates. So, for example, if our estimate of the beta 0 hat is here, then we know that we could draw, if we draw a lot of these or redo the analysis. For example, this might be the intercept we get from picking 100 businesses and doing the analysis. Then if we redo the analysis, we know that these estimates, they should have like a normal distribution, right? They should be normally distributed, which means that even though we do not know the true value of beta naught, this is the true value, we know that if we redo the experiment, we should get some values around this true value, and these should be normally distributed. Okay, so we can think of the beta hats as draws from this normal distribution, because we are using the central limit theorem, because we have a lot of data, and then we can just look at the estimates and we can just like draw the normal distribution around this estimate. Okay, this is a really powerful tool, because if you look at it, then this, the height here should be the same as the height here, and then we can just use our estimate, the normal distribution, and we can estimate the probability that the true beta is within a certain range of our estimate. Okay, we'll get back to that when we do hypothesis testing, but this is probably the most important reason why we need these assumptions. Because if we do not have these assumptions in place, then we cannot trust our estimate, the beta hat. And secondly, these assumptions help us to understand the circumstances in which might pose problem for our estimate or OLS estimation of these slopes and the intercept. Okay, see you next time.